Okay. All right. Yeah, that's fine, Sega. That's fine. That's fine, Matthew. Okay, Christy, no problem. I'm just looking at a few of the comments. Yes, yes. Okay, so section 4.4, we talked last time about bases, section 4.3, and section 4.4 deals with coordinate systems. So let me go ahead and bring up my example here. And let me give you a moment to copy this example down. Okay. Okay. Okay, and so of course I'll make the assignments and the exam available right after class, but during class I want students to be focusing on the lesson. And um, all right. All right, so in this problem, coordinate systems, section 4.4. So you're accustomed to you're accustomed to That's okay, Binyam. So this coordinate system, where you have the x-axis and the y-axis, okay, or I guess in this case we could call it the x1 axis and the x2 axis. This is what you're used to. This is what you're used to. And of course, in 3 dimensions, it would be the x, y, and z axis. Now, of course, along these axes, I can draw vectors. Okay, that one looks a little big, but we can fix that. Okay, and Call this, oops, hold on. I see the problem, one moment. Okay. One moment. Okay, we call that the E1 vector. That vector goes to 1, 0. And this here is the E2 vector. And that goes to 0, 1. Okay, and so we call this, I mean, well, this is the coordinate system you're used to. I mean, like when you dealt with like vectors with I and J, okay, I is 1, 0, J is 0, 1. You know, why is that? Why do we have to why do we use those two vectors? And you know, any vector in R2 can be written as a linear combination of these I, J vectors. Or in this case, well, they're unit vectors, and that makes it easy, Binyam. That's right. So any vector in R2 in two-dimensional space, in R2, I got to be careful, in R2, any vector can be written as a linear combination of these E1 and E2 vectors. So we call those two vectors, E1 and E2, a standard basis. It's the standard basis. It's the basis you're used to. Okay, you're used to that. So like for instance, like this vector 1, 6 here. Okay, this vector 1, 6. How do we understand 1, 6? Well, 1, 6 is equal to 1 times the 1, 0 vector, 1 times E1, plus 6 times the E2 vector, which is 0, 1. So it's a very convenient basis for two-dimensional or three-dimensional spaces or four-dimensional spaces. I mean, it's very convenient to use these unit vectors that fall along the axes. But sometimes you have applications where it's not always most convenient to use the standard basis. Okay, so, and you'll see an example of this pretty soon. But in this problem, what we're going to do is let's suppose that we have a different basis for R2. Okay, a different basis. Let's say the basis vectors that we're going to use consists of the basis vectors 1, 0 and 1, 2. All right, and we have this vector x equals 1, 6. And we want to ask ourselves, what are the coordinates of this vector x 1, 6 relative to this new basis b, Okay. So that's the question we're asking here. So what do we have to do here? I mean, what do we have to do? Well, let's go to the solution. again, we're trying to find the coordinates of this vector x relative to the basis b. The coordinates of the vector x relative to the standard basis are 1, 6, right? But what would the coordinates be relative to this new basis? So what we have to do is we have to find C1 and C2 such that 1, 6 equals C1 times the B1 vector plus C2 times the B2 vector. Okay. I mean, an analogy is if we think it back to the standard basis, we have no problem in, 1, 6 is equal to 1 times 1, 0 plus 6 times 0, 1. Okay, and that's, of course, 1 times the vector E1 plus 6 times the vector E2. So we have no problem thinking about the vector 1, 6. The coordinates are 1, 6, but the coordinates are 1, 6 relative to the basis consisting of E1, E2 vectors. That's the standard basis. So now I'm asking the same question, but I need to find coordinates C1 and C2 such that 1, 6 can be written as a linear combination of these new basis vectors, B1 and V2. And so this produces this vector equation. And for these kind of problems, for this kind of particular question, you start off with the vector equation. And then the vector equation will reduce to an augmented matrix. Okay? But I'm saying, like, if this problem were on, like on your next exam, something like this, you have to start off with a vector equation as part of your work, because that justifies that you understand, the concepts. Okay, and then from there you get to the matrix. So okay, I'm going to solve for C1 and C2. So this is an easy matrix. Don't need MATLAB here. Just some simple row operations. So what I do is I take the second row, multiply it by a half. Trying to write very neatly here. I think it's fine. Okay, and put the result in the second row. Okay, and then of course I want a 0 where that 1 is, so I'm going to use the 1 below it as a pivot, and I'm going to take the second row, multiply it by -1, and add that to the first row. And then that result replaces the first row. All right, are there any questions so far? All right. Well, okay, so now we know what C1 and C2 are. C1 equals -2, and C2 equals 3. And so the coordinate vector of the vector x relative to the basis b is going to be -2, 3, the vector -2, 3. And we denote coordinate vector using this notation. This is the notation we use to denote a coordinate vector. It's the vector x relative to this basis B. We're not operating now in the normal, the standard basis. We're operating in this new basis. So with respect to the new basis, the vector 1, 6 has coordinates -2, 3. All right, are there any questions? Are there any questions so far? Make sure we're good here. Yep. All right, well, if we're good with that, I think it's helpful to have a geometric feel for these new coordinates. So I'd like to go to the next page and show you a nice picture. Is everybody okay now with does anybody need more time to copy, or are we okay? Okay, very good, very good. All right. Well, then let us move on. Excellent, excellent. Okay, here's a picture. And what I've done is I've drawn the basis B. I've drawn the vector x. So the vector x, okay, the vector x goes to 1, 6, right? That's the coordinate. For my vector x. B1, that vector, was 1, 0. And B2, okay, hold on, that vector was 1, 2. Maybe I'll talk about the diagram a little bit and then let you copy it. Okay, it might be a little easier that way. On here. Okay, so please, no writing on the diagram. Don't. My beautiful diagram here. So B1. Now, what was the coordinate vector of x? Thank you, Binyam. I agree. Coordinate vector of x relative to the basis B. Relative to the basis B, though, is -2. Thank you. -2 and 3. Okay, so what I'm going to do is I'm going to start from the origin, but the first thing I'm going to do is apply the second coordinate 3. The second coordinate 3 gets applied to the B2 vector. Okay, so the B2 vector, we just use this thing here. Here's B2. Well, if we go out this far, that's 2 B2 units. And if we go out this far, now we're at 3 B2 units. But we're not at 1/6 yet. To get to 1/6, now we have to apply. Now we have to apply. I go to the left. Hold on here. I go to the left 2, -2. So -2. But I apply the -2 to the B1 vector. The B1 vector goes to 1, 0. So negative of that would be pointing in the direction of -1, 0, right? So I go -1, -2. And that gets me to the vector x. So relative to this basis B here, right, it's negative, it's negative the vector x. Hold on. Get this thing off. Hold on. One moment. The vector x is equal to -2 times the vector B1 plus 3 times the vector B2. But what I did was I applied, I could have done this several ways. I chose to do the 3B2 first and then add the -2B1. But I could have done -2B1 first. If I'd done that, let me show you how that would go. If I'd done that. If I'd done -2B1, okay, starting from the origin, okay, it would be -2B1, and then I go 1, 2, hold on, 2. It's not perfect, but you get the idea. 3B2. Let's see, Binyam says the new vector goes up the coordinate plane by a scale of 3 relative to B2, and then goes to the left by a scale of 2 relative to B1. That's exactly correct, Binyam. Exactly correct. Well, you said a scale of 2 to the left, so that's fine. That's fine. Yeah, it's exactly right. So we don't have to use Cartesian coordinates. The Cartesian coordinate system is based off of standard basis E1 and E2. We don't have to use Cartesian coordinates. Sometimes that's not the most convenient form to use. All right, are there any questions on that? Can this be done on polar coordinates? I do not think so, Binyam, because polar coordinates are based on circles, and yeah, I don't believe so. Like rotations and stuff. Got to be a little careful. I've not seen it done before. I'm going to show you that. Mikhail's wondering what's an example where Cartesian coordinates are less convenient. I'll show you an example of that. And I want to show you just a little something else regarding this example. But are there any questions? May I move to the next page? Okay, Sega's good. Thank you, Sega. Thank you, Christy. Thank you, Devahar. Thank you, Matthew. All right, Kevin, very good. All right, so a little bit on notation here. Thank you, Binyam. A little on notation. So we, of course, can think about, I mean, you know, the vector 1, 6 is equal, as you know, hold on, I gotta get this. The vector 1, 6, as you know, equals -2 times 1, 0 plus 3 times 1, 2. Okay, and that's -2 times B1 plus 3 times B2. But remember, because of matrix multiplication, you could think of this linear combination of vectors as a 2 by 2 matrix times a vector. The second vector would be your coordinate vector of x relative to the basis b. That would be the vector. And the matrix, this matrix here, is called P sub b, or P, it should be P subscript b. And what that matrix is, it's the matrix, it's called the change of coordinates matrix. Change of coordinates matrix from the base B to the standard basis. Okay, that's what that's called. The curly line, script B, means a set. But you know, you could use I mean, the book traditionally uses a script B, but I've also, their B looks a little different than mine, but it's just to denote a set. The script B here, the script B set is equal to the set of vectors B1 and B2. And that B1 and B2 form a basis for R2, just like you know the standard basis that you all know and love. That forms a basis for R2. The basis script B, which consists of vectors 1, 0 and 1, 2, that's also a basis for R2, because vectors 1, 0 and 1, 2, they're linearly independent, and any vector and the span of and those span of those two vectors will equal R2. Any vector in R2 space, in that two-dimensional space, can be written as a linear combination of B1 and B2. Okay. Are there any questions on that? So our change of coordinates matrix from base script B to the standard basis transforms the coordinate vector into a vector x, being, you know, that's what it's doing. That's what it's doing. And of course, I'll note here that you know, the vector x equals P sub b. Sometimes I call that my peanut butter matrix. I don't know. It just helps me kind of, I don't call it that, but I think about it in my mind. All right. So let me ask you, could we solve for x sub b, what would the coordinate vector of x relative to the basis b equal in terms of a matrix product? The coordinate matrix P sub b is square. Is it invertible? Is P sub b invertible? Absolutely. Absolutely. So how would you write? Right, Binyam, the determinant's not zero. So by the invertible matrix theorem, that square matrix is invertible. So how can we solve it? What would the coordinate vector x relative to that base script be equal? That's right, Binyam. That's right. It's going to equal the inverse of the script of the inverse of my coordinate matrix times the vector x. Just multiply on the left both sides by the inverse of the coordinate matrix. And so now you have a way, that's a way to get your coordinate vector. So we solved a vector equation, but here's another way. Of course, the issue is you have to get the inverse of the matrix of that coordinate matrix, but it's not too hard. It's a 2 by 2. All right. Are there any questions? That's right, Binyam. Yep, that's right. Everything's connected. Every time you learn a new section, it connects back to an old section, which in a sense makes linear algebra, sometimes it can be a little more challenging, right? Because it isn't like you learn a section and it goes away, right? Or like in calculus 2, I teach that, we learn about arc length, but once you learn about arc length, you go to the next section and there's nothing really relates to arc length. So, but all right, let's go to another example. Are we good? We'll move to the next example. All right, very good, very good. So let's look at an application of this. Why is this important? We've been using the standard basis to work in R2 and R3 space our whole lives. Why would we need to, why would having using a different basis help us? Well, here's an example. So this is actually based on 2 exercises in your textbook, exercises 37 and 38. And how many are, hold on here. How many have maybe looked at lattices in chemistry? Okay, high school, Binyam's seen it in high school. So, there's crystal lattices for like, this is The crystal lattice for titanium, okay, has this hexagonal structure. So, okay, Divahar remembers. Right, so what I have here, and this is going to be in the recording, I'm not expecting you to copy down these figures, but what we have here is we have the crystal lattice of titanium, and it has the hexagonal structure shown in the left figure. And the vectors, these three vectors here, form a basis for the unit cell shown in the figure. Okay, so where are they getting this from? Well, what they've done is I want to say this the right way here. All right, I'll have to. So what I'm going to do is I'm going to, in the lattice, delineate a unit cell. Okay, that's a unit cell. Yes, and this is scaled well. Hold on, Binyam. Hold on. It's so what they have here are three dots. And what they're doing is on the right here, they're taking out that cell from I want to say it's the right way. Hold on. Okay, they're taking out that cell. It's a parallelepiped. Okay, it's a brick, and they're extracting it and showing it on the figure on the right. And they have these basis vectors U. They have these basis vectors U, V, and W, and then there's the origin. And these numbers here are in terms of like your standard lengths that you would deal with in R3, standard basis. Okay. What I'm trying to say is the distances. Don't think about standard basis. Just think in terms of distance. Okay. Distance is distance. So I got on the right here. I got a U, V, and W, and I'd like to label with these three vectors. I would like to label U, V, and W. So like V, what would make the most sense for V? Would it be the first vector, second vector, or third vector? Look at the picture on the top right. Yeah, that's right. It has to be, second vector has to be V. Because, here's V, right? Hold on, kind of going back and forth. Here's my V vector. It just goes to the right. So 0, 3, 0. Second coordinate is like the Y in the Y direction, Y-axis direction. What about W? What's W going to go with? The vector W in the picture. That's the third one. Good, Solomon. Hold on here. Because the third vector W, all it does is it goes up. from the origin, it just goes up. And then the last vector u would have to be the remaining one. Now the last vector, the vector u, doesn't go up or down, but it goes forward 2.6 units and to the right negative 1.5 units. So that's going to be your w, or your u, I should say. Sorry, u. Are there any questions on that? Well, since the cell is constructed the way it's constructed, it could be very convenient to use vectors that are on the lattice, that are on the unit cell. So u, v, and w, they form like the boundaries of the cell. And what we want to do is, relative to that basis, relative to this basis, one atom in the unit cells located at the site a half, a fourth, a sixth. A half, a fourth, a sixth. Okay. So that the half, fourth, and a sixth, okay, means that like the one half here, let me just keep my colors a little different. The one half, and by the way, you can see it right here in the picture. Here's the cell they're talking about, right there. Okay, they got a little dashed line going up from the base to that blue point there. So when they say a half, when they say relative to this basis, one atom in the unit cell is located at the site, one half, a fourth, and a sixth. With the half, what direction are you moving? Like you're going a half. Like what's a unit in that direction? That's right, Mikhail. The u vector is like a unit. I mean, it's not like the unit we're used to. A unit vector, what you're used to is just 0, 1 or 1, 0. That's a unit vector. But in this case, quote unit vector is for u. It's 2.6, negative 1.5 and a half. So you're going to move 1/2 unit in the u direction, in the u vector direction. And then the fourth, you're going to move a fourth unit in the what direction? In the v direction. But you're moving 1/4 of a v. You know what I mean? 1/4 of the v vector. So if you think of the v vector as a unit relative to that basis, you're moving 1/4 unit. And then finally, the last number, the 6, you're moving in the direction of what vector? The vector w. So you're moving 1/6. Think of the w vector as a unit. You're moving 1/6 units in the w direction. So this here, what is this really? I mean, they didn't say what this is, but what is 1/2, 1/4, 1/6? What kind of vector is that? Is it equal to x? Would that be right? Is x equal to 1/2, 1/4, 1/6? What do you think? So I have smart people I'm getting different answers. I mean, does x equal a half, a fourth, a sixth? No. A half, a fourth, and a sixth equals, it's the coefficients. That's right, Benjamin. And this is a coordinate vector. So a half, a fourth, and a sixth is a coordinate vector of x relative to basis B. Well, of course, it would help to know what x is, but you know that's, I mean, what we're going to do, I'll move to the next page. Well, no, I'll go down a little bit. What we're doing is we want to determine the coordinates of this site relative to the standard basis in r cubed. So when they say that, then you know the coordinates of the site relative to the standard basis in r cubed. I want to say this the right way. That whole thing, okay, the coordinates of the site relative to the standard basis in r cubed, what vector would that be? What vector would that be? So relative to this new basis, one atom in the unit cell is located with coordinates 1/2, 1/4, 1/6. Now what we want to do is determine new coordinates, the coordinates of this site relative to the standard basis that we know and love. So how do we denote a vector in r cubed? How do we denote it? Is it, you know, what would it be? Well, I mean, okay, it would be, so coordinates means coordinate vector, right? So coordinate vector, and relative to what basis? I gotta put in some basis vectors here. Gotta put in some basis vectors. How many vectors are going to be in the basis? How many? Okay, 3. And we want the coordinate vector relative to the standard basis. Well, Robin, the u, v, and w is the basis. It's the hold on here. Let me just good. So script B consists, that basis is, I don't know why that comes up. It happens, just ignore it. U, V, and W. I don't know why that pops up there. So everybody, just ignore that line. Hold on. Hold on. Let me write this again. I'm not going to write all of it, obviously, but I don't know. It happens sometimes. So please, nobody write, nobody do anything. Okay, that's where my script B equals U, V, and W. And this is the U, this is the V, this is the W. Okay, and so relative to this basis, and when I say this basis, I mean this basis here, one atom in the cell is located at 1/2, 1/4 of 6. That's the coordinate relative to basis B. But now what we want to do is we want to determine another coordinate vector. Determine the coordinates of this side relative to the standard basis. So I'm going to write down another coordinate vector. Okay, another coordinate vector. And it has to be subject to a basis. And so what I'm asking is, what are the vectors in the standard basis? In R2, what was the standard basis? If you look back in your notes for R2, what was the standard basis? E1 and E2, all right? Good, Solomon. But what would the standard basis be here in R3? E1, E2, E3, exactly. E1, E2, and E3. All right. Are there any questions? Let me make that a little nicer here. The 3s are sometimes a little hard to write, but Kevin's good. And you know what we call this? We're just going to call that vector x. So the vectors that you've been using your whole life, vector x, vector y, vector, you know, but we're calling this vector x. The vector x, now you think of that vector x as a coordinate vector relative to the standard basis. You've been doing this your whole life. You just didn't know you've been doing it. When you draw vectors, when you draw the vectors and based on the coordinates are based on the standard basis. And so the vector x is equivalent to the vector x relative to this standard basis, E1, E2, and E3. How many think that's kind of cool? Yeah, I think Christy likes it. I hope that's a happy face. I don't know, but it's amazing. And so now we want to find x, and Mikkel's right. Mikkel's right. Okay. We already know the coordinate vector of x relative to the basis script b. We wrote that down, and so the vector x, okay, which is the coordinate vector of x relative to the standard basis, that's just going to be the change of coordinates matrix with respect to basis b, script b, times the coordinate vector of x relative to basis script b. And the b should go on the outside, right? So let me fix that. We use script b to denote sets because capital B stands for like a matrix. A capital A stands for matrix. So we try to distinguish our things. And of course, the change of coordinates matrix consists of columns U, V, and W. which Mikkel noted a little earlier in the chat window. So you have a 3x3 matrix times a 3x1 matrix. And when you work it out, you're going to get 1.30 and 0.8. So this is an example where we're taking a matrix times a vector, right? Taking a matrix times a vector. I can geometrically have a better feel by writing that matrix product as a linear combination of the basis vectors u, v, and w. How many like going from like x, from x directly to this step? Yeah, yeah. And it's because geometrically it makes sense. You know, it helps you intuitively. It makes sense. Yeah. Thank you, Sega, Solomon, Robin, and Binion. You can see the scaling better. Absolutely, Binion. Absolutely. So see, sometimes different representations of, you know, we can look at matrix multiplication in like, you know, in this way, and here it's very helpful too. Very helpful too. And so the vector x equals 1.30 and 0.8 relative to the standard basis. If we were to plot an x, y, and z axis, you know, that would be we would be then scaling along those axes to get our result, to plot our vector. And you know, you have to recognize that, you know, that the vector x does equal, I mean, the vector x is equal to a matrix times a vector. So you are doing a coordinate mapping there. What you're doing is you're taking the vector x, and the vector x, okay, lives in some vector space V, and you're mapping it to another vector, coordinate vector, and the coordinate vector in this case lives in R3. Actually, both vectors, hold on, I got to be careful here. Actually, I got that, hold on, one moment. Let me see here. I have that switched. Should be like this. You're taking the coordinate vector and mapping it to the vector x. It's a mapping, right? Every vector x with respect to the standard basis can be comes from a coordinate vector. So all right, are there any questions? Any questions? I'm going to go to the book here and bring a few things up from the book here. But one moment. There might be a question. One moment. Let me bring up the book. Okay, Christy's good. Wonderful, wonderful. just see here, one moment. I want to make sure I write this well. So again, in this problem, you took a vector, coordinate vector in R3, and mapped it into new coordinates in R3. That's what you did. The new coordinates relative to the standard basis vector. So just trying to make sure everything's neat. Okay, and that should be, I like to make sure it's nice and clean. Okay, are there any other questions before we move on? All right, all good. Thank you, James. Thank you, Matthew. Thank you, Kevin. Okay, well, let's move on. And you know, thank you, Robin. Thank you, Sega. All right. So let me see here. In chapter 4. Okay, so yes, Binyam, question? Yes, okay, okay. The overarching theme, well, what we're doing is we're learning that there are different coordinate systems. Just like there are different planets, there are different coordinate systems. And coordinate systems, sometimes the standard coordinate system, you know, X, Y, Z axis or the standard basis, sometimes it's not the most convenient coordinate system to use. This problem where we had the unit cell, the axes did not fall along the X, Y, you know, Z axis. They fell along those in the direction of those basis vectors, U, V, and W. And so in that case, it's more convenient, more understandable to use those vectors as a basis. It's absolutely amazing. It really is amazing. All right, well, let's go. All right, very good. Let me go into the book here a little bit. And one moment here. You're welcome. You're welcome. Yes, Binyam, very powerful tool. Linear algebra is used, oh my goodness, it's used in statistics, it's used, I mean, you name it, it's used. I personally think they should make the course required. See here, in just above example 3, they have, this is sort of what one of the students was asking about, like polar coordinates, and I think it's because of the, you know, thinking about the, like there's polar coordinate paper. How many have seen polar coordinate paper? Maybe. Like you have your standard quadrille rule paper, but then there's polar coordinate paper that has, you know, like circles on it. I don't know if any of you've seen that, but it exists. But see here in the little picture here, they have, you know, so your standard graph paper, and then here's your graph paper that would correspond in Figure 2 to, you know, to the vectors b1 and b2. That's from the previous example, you know, the first one we did, but, you know. All right. Let's see, you grew up with figure 1 graph paper. You didn't grow up with figure 2 graph paper. But maybe in another world, they use figure 2 graph paper instead of figure 1 graph paper. You see what I'm saying? You see, let me make that a little bigger. Hold on here. Hold on. So what I'm saying is, like, if you think back to the first example, so here, you know, you have your standard graph paper in 2 dimensions is where you have E1 and E2, right? You know, XY axis. But figure 2 is graph paper relative to that basis B that we had, 1, 0, 1, 2. Okay, that's your let me just see here one moment. That's your graph paper for that basis. So, you know, maybe on another planet they use the basis in figure 2. But we use the basis in figure 1. Wouldn't that be kind of amazing? Huh? Yeah. You know? All right, I think I'm getting let me see here. I don't have everything. Hold on one moment. Got a few too many windows open here. Let me just go back to where you all are. Hold on, where are you? Yeah, absolutely. Solomon and Christy are liking it. Robin's liking it. Okay, so let me keep going here now. Trying to. Okay, so we talked a little bit about crystal lattice issues, and we talked a little bit, you know, about you've seen this from the examples. Coordinate mapping. So this is really a transformation. Let's just keep going here. Okay, so you could, like in example 5, they say, suppose B, script B is the standard basis for the space of polynomials, P sub 3. That is, let script B equal 1, comma, t squared, comma, t cubed. A typical vector in the P3 space would have this form then. Any vector, any third degree polynomial can be written as a linear combination of the basis vectors 1, t squared, and t cubed. So the polynomial space, P sub 3, is I mean, any vector in that space would have this coordinate vector here. A naught, or A sub 0, A1, A2, A3. Okay, so they say the coordinate mapping. Well, let's make sure you're comfortable with that. Does everybody see that okay? Okay, thank you, Christy. Are there any questions? All right, Kevin's good. All right, well, let's continue then. So we call this coordinate mapping, again, here, you are, let's say this the right way. Hold on here, one moment. Okay, so you have an isomorphism from the polynomial space onto R4. So in other words, you have P sub 3 is the set of all third degree polynomials. That space, okay, that vector space. It's a vector space, right? Well, you can map any third degree polynomial in that space to a coordinate in R4, because any polynomial, any third degree polynomial can be represented with the four coefficients, well, four numbers, A0, A1, A2, A3. It's the A0 and the coefficients A1, A2, A3 that uniquely determine the polynomial, right? I mean, the one, the basis, the one, the t squared, the t cubed is always there. But any polynomial can be written as a linear combination of those, of 1, t squared, t cubed. And the linear combination is a sub 0, a sub 1, a sub 2, a sub 3. We call that an isomorphism. It's a one-to-one onto mapping. That's what an isomorphism is. If you give me any coordinate in four-dimensional space, I can associate that coordinate with a polynomial, with a third degree polynomial. Okay, does that make sense? Are there any questions? All right. Well, let's move on then. Let's move on. So just go to the next page here. So they have a little picture here where the polynomial space, third degree polynomial space, is isomorphic to R4. I don't really know if you need that picture, but they're just saying, you know. Example 6, they want you to use coordinate vectors to verify that the polynomials 1 plus 2t squared, 4 plus t plus 5t squared, and 3 plus 2t are linearly independent in the second degree polynomial space, P sub 2. So, you know, the thing is, you know, if these three vectors are linear, oh, well, they're saying they want to use coordinate vectors to verify that the polynomials, these three polynomials, are linearly dependent. Dependent, I might have said independent, dependent. So how can you show that? Well, what they do is they write down the vectors corresponding to each polynomial. They have that here in this this matrix. So let's make sure you're comfortable with that. And what they're doing is they're solving the system a times the vector x equals the 0 vector. And we want to see if our solution is going to be trivial or non-trivial. And in this case, we have a row of zeros on the bottom. Okay, so even though we get a consistent system, is the solution going to be trivial or non-trivial? Non-trivial. That's right. That's right. Why is it non-trivial? What are we in that system? What are we going to have? There's a free variable there. That's right. Infinite solutions. That's right. So I mean, all that matters is that, you know, I mean, the trivial solution is always a solution, but if other solutions exist, then that's a problem, right? Then you don't have linear dependence. Okay. Now, the last example, example 7, concerns a plane in R cubed that is isomorphic to R squared. Okay, so here you have a plane in R3, but it's isomorphic to two coordinates. So they let V1 and V2 be as you see them, and they let X equal 3, 12, and 7. Okay, so we're looking at example 7 here. Then script B is a basis for the span of V1 and V2. Well, that makes sense because V1 and V2 are linearly independent, and the span of those vectors is equal to H. So so that's fine. We want to determine if the vector X is in H, in that subspace, and then find the coordinate vector of X relative to the basis B, script B. So again, here comes that vector equation. If we're going to find the coordinate vector of X relative to the basis script B, we need to set up a vector equation. We do that first. And then, from there, we solve a system. An augmented matrix, a system of equations. But are there any questions so far? I want to make sure you're comfortable. I want to make sure I'm not moving. I think I'm moving okay. I think I'm pacing myself okay. But let me know if you have any questions. All right, Christy, thank you. Yeah, it's, you know, it's, it takes a little time to feel it, but sure, it's, some folks it takes longer than others to understand, but that's okay, so long as you understand eventually, right? So long as you understand in time for the exam, right? All right. Okay, all right, that's fine, that's fine. So what is C1 equal to here? What is C1 equal to? C1 is 2, and C2 is 3. That's right. That's right. So you see, what you've done is, even though the plane lives in R3, the plane is simply a linear combination of the V1 and V2 vectors. That's what it is. And so any linear combination of the vectors V1 and V2 is going to put you back into the plane. There's a great picture here on the next page. Let me show you the next page. Okay, so here in three-dimensional space, they've drawn x1, x2, x3, and they've drawn the basis vectors v1 and v2. Okay, and actually, it's actually, let me see here. Well, they've drawn them, okay? They've drawn them. V2 makes good sense to me because V2 is -1, 0, 1. So you move 1 back on the x1 axis. You don't move along the x2 axis, and you go up 1. So V2 makes good sense. V2 makes good sense. V1, well, that's fine. 3, 6, 2. We know that's got to fall in the first octant because all the coordinates are positive. So what they do is they take 2 times V1, okay, because the coordinate vector of X relative to the basis B vectors that generate that plane are 2, 3. So we go 2 V1 units plus 3 V2 units, and we end up with the vector X. So you see, we have a sample here, an example of a plane in R cubed. It's isomorphic to R squared, meaning that any point in the plane, any three-dimensional point, any point, a point in the plane has three coordinates, right? But it's isomorphic to a vector with two coordinates. See? It's isomorphic to a vector with two coordinates. So you have a one-to-one onto mapping for vectors in R3 into vectors in R2. But of course, the vectors in R3 aren't all the vectors in R3. It's just the vectors in that plane. Because the plane is a two-dimensional subspace of R3. That's the key. The plane is a two-dimensional subspace. And you're mapping that two-dimensional subspace onto another two-dimensional subspace. Okay, does that make good sense? Are there any questions on that? Yeah, I agree, Binyam. Oh, snap. I hope that means cool. I think that does. Okay. Yeah. Very nice. Absolutely. Absolutely.